This is example 9-5, where we have this connection between where two pipes come together. One of the pipes is containing gasoline or kerosene, and the other one has crude oil, and they're mixing, and they're flowing together, and then they exit through another pipe. And the question now is, do these actually mix, which means there's turbulent flow, or do they not mix because it's laminar, right? So to do that, we'll have to look at the Reynolds number. So just for our own reminder, right? So the Reynolds number is going to be the density. Now in this case, it's the density on the way out. So it would be rho m for mixed, right? So this would be, we can say this might be oil, this might be kerosene, and this is definitely going to be mixed. Then we want to have that multiplied by the average velocity at the pipe that's going out. So we'll say V mixed. And then the characteristic length scale is going to be the diameter at the mixed level, right? So we'd have dm, which is 60 millimeters in this case. And of course, all of this is divided by mu of the mixture. Now, what do we have? What don't we have in this equation? We have the viscosity of the mixture that's given to us. We're given the diameter of the pipe, but we're not given the velocity there or the density there. But we can easily calculate those, right? So we can say for the velocity, we can just use continuity, right? So we can say from continuity, right? We can say, well, we have flow going in. That means my A vector is going to point this way, this way, this way, and of course there's going to be flow out here as well. Right, so that means at our oil location, right, so we have a negative sign because the two vectors are in opposite directions. That'd be A oil times V oil. Same at the kerosene place, A kerosene times V kerosene. And then at the mixed end, we get a positive term because the vectors are in the same direction. So we'd have A mixed times V mixed, and that's equal to 0. So we're looking for V mixed, so we can easily solve that. V mixed is then going to be A oil times V oil plus AK times VK divided by A of the mixed location. All right, we know those are all pipes that are circular, so we can say that'd be pi over 4 times D oil squared times V oil plus pi over 4 times dk squared times vk divided by pi over 4 times d mixed squared. Of course, that means we can get rid of all of those pi over 4s. They just cancel out. So we're left with d oil squared times v oil plus d kerosene squared times v kerosene divided by d mixed squared. All right, another thing that we can notice is that the diameter and the velocities at the oil and the kerosene are the same. So we can just say this all would be 2 times, let's call it d oil kerosene, so OK squared v OK divided by dm squared, or write this in a little slightly nicer way, would be 2 times dok squared over dm m squared times VOK is equal to 2 times DOK over dm squared times VOK. All right, so with that we have our velocity. So we could plug that in, but we're still missing the density. So we can get the density by doing continuity with mass flows, right? So we know that the mass rate of oil, m dot oil minus m dot kerosene plus m dot mixed has to be 0, right? The inflows and the outflow. That means we can solve that for m dot m is m oil plus m kerosene. And then we can plug that in, right? So that's the same as saying rho mixed times V mixed times A mixed is equal to rho oil times V oil times A oil plus density of the kerosene times V of the kerosene times A of the kerosene. That means we can write out what those areas are. So we have rho m times Vm times pi over 4 times dm squared equal to rho oil V oil times pi over 4 d oil squared plus rho k times Vk times pi over 4 times dk squared. All right, that's a lot of stuff right there. So of course we can divide all of that by pi over 4, right? Because all this, we have it on both sides, right? So that means we get that rho m times Vm times dm squared is equal to rho oil times V oil times d O squared plus rho k times Vk times dk squared, which means we can solve this for rho m, which is what we're looking for, right? So we can say rho of the mixture is equal to that big term, so rho oil times V oil times d oil squared plus rho k times Vk times dk squared divided by rho mixed times V mixed. Oh, not rho mixed, that's what we're looking for. So V mixed times D mixed squared. All right, so it's two things we can notice here. The first one is, of course, that our velocities and our diameters are still the same at the oil and at the kerosene site, right? So we can say, if we pull that out, we'd get VOK times DOK squared times rho oil plus rho kerosene. And then we can plug in what we found for the velocity, right? We found that the velocity, where do we find this? Up here, right? That was 2 times DOK over dm squared, DOK over dm squared times VOK, right? That's our what we found right there. And that still is equal to, is times dm squared. All right, so let's look at this. So we're missing a 2. Right, if we add those, no, not a 2, we're not missing a 2. Let's see. So what do we have? We have a dm squared and a dm squared, so those cancel out. We have a dok and a dok. We have a vok and a vok. So most of what we have cancels out. And so that means our density of the mixed fluid is dO plus rho O plus rho K divided by 2. Now that's not all that surprising, right? If we go back to our figure here, if half of the fluid is coming in with one density and the other one is coming in with another density, and they're coming in at the same rates, right? Then it's just going to be the average of the 2. All right, so we have that now. If we go back to our Reynolds equation, now we have rho m, we have Vm, so we can look if we get turbulent flow or if we get laminar flow. So we can get our Reynolds equation. Our E is equal to our rho mixed times V mixed times D mixed divided by mu mixed. All right, so that means we can plug in all that stuff that we had. Probably need a little bit of space here. So rho m, right, that we just found was rho oil plus rho kerosene divided by 2. That's our first one. Then we have our velocity was 2 times dok over dm squared times vok. And that was our Vm, so we just have to multiply this by dm. And then we divide by mu m, which is given to us, right? So we don't have to change anything there. So let's see what happens here. So those 2's cancel out. We can see that. Rho oil plus rho kerosene. Now here we see that one of the dm's cancel out, so we'll just pull that down there. So we'll leave the dok squared times vok, and we'll divide all that by mu m times dm, right? That's the remaining dm here, and that didn't cancel with the other one. All right, so that means we can now plug stuff in. So we have 880 kilograms per cubic meters plus 810 kilogram per cubic meters. Our diameter out there, this is dok, so that is the smaller one, so that is 0.04 meters squared. The velocity coming in is 0.2 meters per second, right? Those are, you can find those here, 40 millimeters and 0.2 meters per second. And then we're dividing that by the given viscosity, 0.024 Newton seconds per meter squared. And we still have to multiply that by the diameter on the outflow points. That would be 60 millimeters, so 0.06 meters. All right, we plug all that in. We get 375.55, which is of course less than 2,300, which means we have, let's go to the next line, which means we have laminar flow, which means we have no mixing. All right, so our result showed that if we set this thing up, we won't get a fully mixed mixture at the end, but we'll get basically the stream on, like the top half of the stream is going to be oil, and the bottom half of the stream is going to be kerosene, more or less. All right, so that was example 6-5, where we used the Reynolds number to find out if a flow was turbulent or laminar, and we had to use the continuity equation to get there.